Well, students, in the last lecture, we have discussed Taylor's theorem. We'll now pass on to the next section of our chapter 1 on mathematical preliminaries. In this section, we will discuss the notation of big O and small o, and also we will discuss order of convergence of a sequence. Let us take these two sequences, sequence n and sequence n square. We can see that both are unbounded sequences, and of course they both tend to infinity as n tends to infinity. Now the question is, which sequence tends to infinity faster than the other? Well, we can immediately say that n square is going to go to infinity faster than the sequence n. Let us take another example. Take two sequences, 1 by n and 1 by n square. Both are bounded sequences, and we know that both tend to 0 as n tends to infinity. Again, if I ask you the same question, which one tends to 0 faster than the other? Well, you can immediately say that 1 by n square tends to 0 faster than the sequence 1 by n. So once you have these ideas in mind, we are almost through with order of convergence. The order of convergence is all about comparing two sequences converging to same limit in terms of speed at which they converge. What is the tool that we use to study this? Well, these are big O's and little o. Let us define these two notations. Let us take the first one, big O. Let sequence an and bn be sequences of real numbers. Then we say that an is big O of bn, which is written like this. And how is it defined? Well, we will say that an is equal to big O of bn if there exists a constant and a natural number n such that mod an is less than or equal to c into mod bn for all n greater than or equal to n. Let us try to see what this definition means. For that, let us consider an tending to 0 and bn also tending to 0, but bn is not equal to 0 for any n. Then this definition says that mod an divided by mod bn, okay, is bounded by this constant c, right? So I can divide both sides by bn because bn is not equal to 0. That means the sequence an by bn is a bounded sequence. This is an implication of this definition. Now, when this can happen, let us go back to our previous example. We had 1 by n square and also 1 by n, right? So we had two sequences. Let us take this sequence as an and let us take this sequence as bn. And you can see that when you divide an by bn, we get 1 by n, right? So that always remains bounded, say by 1. In fact, it goes to 0. So I can take my c as, say, any number which is greater than 0. Let me just take as 1. So what made this term in this example a bounded quantity? Although bn was going to 0 and bn is sitting in the denominator, nevertheless this term did not blow up. Why? Because an was going to 0 faster than bn. So it was always going faster than bn, and that made your sequence an by bn to remain bounded even though the denominator bn was going to 0, right? Let's take another example. An is equal to 1 by n and bn is equal to 2 by n. Okay. In this case, an by bn is equal to 1 by 2, right? So in this case, both these sequences are going to 0 and they both go in the equal speed. Just intuitively speaking, both are going in the equal speed, and they therefore compensated each other and made this sequence to be bounded. Well, we can just put any number greater than or equal to 1 by 2. Let me just take 1 by 2 itself, and that is the C that is working in this example. So although bn was going to 0, this entire term did not blow up because an was compensating bn and made this sequence an by bn bounded, right? So from here you can see that this condition says that the sequence an is either going faster or at least as fast as bn to the limit to where they are converging. Okay, in case if they are converging to same limit, then this definition says that an is either going faster to that limit than bn or as fast as the speed of the bn. That is what the interpretation of this definition. So I can say that if bn is not equal to 0 for every n, then this notation means the sequence an by bn is a bounded sequence. Intuitively, what it means is that the sequence an goes faster to the limit than bn or at least as fast as the bn goes to the limit. That is the intuitive idea from this definition. Now let us go to the definition of little o. Here we say that the sequence an is little o of bn. Notationally, it is denoted with a small o here. If for every epsilon greater than 0, there exists a natural number n such that this condition holds. Try to see the difference between this definition and the big O definition. Big O definition says that there exists a constant c greater than 0 and then it follows with this, right? That is what the big O is. But here what we say is for every epsilon greater than 0, there exists a natural number. So what we say from by here is you have as usual two sequences an and bn. Just consider the case when both of them are going to the same limit. Okay. In particular, let us take both of them are going to the limit 0. Then as long as bn is not equal to 0 for every n, then we can divide both sides by bn just like what we did in the last definition. An by bn is actually converging to 0 as n tends to infinity. That is what this definition means. Why it is so? Because what we say is you give me any epsilon, I can find a n such that I can pack these numbers bn something less than or equal to the epsilon that you gave me for all n greater than or equal to capital N. That's what the definition says in this particular case. Now you see, you may give very small epsilon to me, even then I should be able to pack this number less than this. Okay. You see, for every epsilon greater than 0. So you may give me epsilon is equal to 10 to the power of -5 or -10 or anything, whatever may be the epsilon you give, I should be able to pack this number within that small bag epsilon, right? For a large enough n, as I go larger and larger in the sequence, I should be able to pack these numbers into that small bag. Whatever may be the small bag that you give, I should be able to pack all these numbers which are coming with a larger and larger indices, right? There are infinitely many such numbers, but still I can pack within this small bag. How can I pack that? Provided this number, as n tends to infinity, this number should go to 0. Then only I can give you guarantee that I can pack all these numbers into this small bag, right? Therefore, this definition means an by bn is actually tending to 0 as n tends to infinity, okay? Again, going back to our example, let us take an is equal to 1 by n square and bn is equal to 1 by n. Then you can see that an by bn is equal to 1 by n. So now you give me any small epsilon, whether these or even something less than that, I can always find a large enough n such that this is less than or equal to that epsilon for all n greater than or equal to that large number that I have chosen, right? So although the sequence bn, which is sitting in the denominator, is going to 0, who made this all this entire numbers to be packed within this small bag epsilon? It is because an is going strictly faster than bn, right? And therefore it reached 0 before bn, intuitively speaking, and that made this sequence to actually go to 0, although the denominator is going to 0, right? An went and nullified this entire number. So that is what is the idea of small o. Whereas you take another example, an is equal to 1 by n and bn is equal to 2 by n, you see that an by bn is equal to 1 by 2. Now, if I give you any epsilon less than 1 by 2, say for instance, epsilon equal to 10 to the power of minus 5 I give, I cannot fulfill this condition, right? So it cannot be less than or equal to 10 to the power of minus 5. That is not possible for however large n you take, right? So what made this sequence to violate this condition is because your an was going as fast as bn, and thereby it is compensating this 1 by n with each other, okay? That is making this sequence, although to remain bounded, but it does not allow this sequence to go to 0. Therefore, small o is demanding something more than what big O demanded. The small o says that an is equal to small o of bn if an strictly goes faster than bn. That is the intuitive idea behind small o. Big O means it can go faster, or at least it should go as fast as bn. An should go at least as fast as bn. Whereas small o demands more stronger condition that an should go faster than bn. So small o implies big O because it is already sitting in the condition of big O, whereas big O not necessary implies small o. Okay, the example is the second example. Well, so far we have discussed the concept of big O and small o for sequences of real numbers. We can easily see that these ideas can be extended to study functions where two continuous functions are given and we are interested in seeing which function approaches a limit faster than the other. In this context, let us define big O and small o for functions. Let us start with big O. Let x naught be a real number and f and g are continuous functions defined on a same interval which contains x naught. Then we say that f is big O of g as x tends to x naught. Notationally, we write it as f of x equal to big O of g of x as x tends to x naught. Whenever we write this notation, we have to always write this. Now, when we will say that f is big O of g, if there exists a real number c and a real number delta such that modulus of f of x is less than or equal to c into modulus of g of x whenever x minus x naught is less than or equal to delta. That is, we have this point x0 and we are interested in seeing how two functions f and g approaches to the point, say, alpha as x tends to x0. So you take x tending to x0 and see how f tends to alpha and g tends to alpha. So this means that you sit in a small interval x0 minus delta to x0 plus delta and see whether this inequality is satisfied. Well, I leave it to you to understand what it means. From our discussion in terms of sequences, it will be very clear for us to see that when g of x is not equal to 0 for every x, then this big O notation precisely means that this function f of x divided by g of x is a bounded function, at least in this small neighborhood of x0. Now let us pass on to the definition of little o for functions. Let x0 be a real number and let f and g be continuous functions defined on an interval containing x0. Then the function f is said to be little o or small o of g as x tends to x0. Notationally, we write f of x is big O of g as x tends to x0. If for every epsilon greater than 0, there exists a real number delta such that this inequality should be satisfied in a small neighborhood of x0. Again, from our discussion on little o for sequences, we can see that whenever g of x is not equal to 0, for every x, the little o notation is equivalent to saying that the function f of x divided by g of x tends to 0 as x tends to x0. So what is the intuitive idea behind big O on small o for functions? Well, the intuitive idea remains the same. In fact, from the definition, you can see that small o always implies big O. Is the converse true? Well, I leave it to you to find an example to show that the converse is not true. How will you construct such an idea? Well, you can construct it if you can clearly understand the intuitive meaning of big O and small o. Just take f of x tending to 0 as well as g of x tending to 0. Just take any function f such that f of x tends to 0 and also another function g which is also tending to 0. Both are continuous, of course, as x tends to some point, say a. Then from the definition, you can understand the intuitive meaning that big O means f of x is tending to 0 at least as fast as g of x tending to 0 as x tends to a, right? It means either f of x is tending to 0 faster than g tending to 0 or at least as fast as how g is tending to 0 as x tends to a. Similarly, small o means f of x is tending to 0 strictly faster than g of x tending to 0 as x tends to a. Therefore, small o is demanding something stronger than the big O. That is why small o always implies big O. Let us now go back to our previous example discussed in our last class on Taylor formula for cos x about the point a equal to 0. If you recall, we have the Taylor polynomial for cos x of degree 2n is given by this, and the remainder has been taken in this form. If you recall, we have taken cos x as 1 minus x square by 2 plus x power 4 by 4 factorial. And then when it comes to the remainder, the Taylor's expansion actually suggests us to take the remainder as sine c by 5 factorial into x to the power of 5 for some unknown c, but we decided to take, instead of this, cos some c dash. It may be in general different from the c which comes here, but let me just use the same notation c here, with the caution that this c may not be the same as the c which comes from in this reminder. Okay, both are unknowns, therefore I don't mind using the same notation here, divided by 6 factorial into x power 6. There I told you that I will give you the reason for why we prefer to take this as the reminder, in especially in numerical analysis point of view. Let us now give the reason precisely after understanding the big O and small o notation. In general, the remainder term we prefer to take is written like this. In particular, when you take n is equal to 2, is what we have precisely written in the last example. What you do is define f of x as this remainder. That is the truncation error. You can see that this entire thing is a fixed number. Of course, we don't know it because c is unknown, but otherwise this is a fixed number, and you have x to the power of 2 into n plus 1 here. Okay, so it is something looks like a constant times x to the power of 2 into n plus 1, right? Where this constant is given by this expression. Okay. As x tends to 0, you can clearly see that fx goes to 0 because this is a constant, and you have x to the power of 2 into n plus 1. So as x tends to 0, this goes to 0, and therefore f of x goes to 0. Now the question is, how fast does f of x goes to 0 as x goes to 0? We can see that f of x goes to 0 as fast as x to the power of 2n plus 1 tends to 0 as x tends to 0, because f of x is constant times x to the power of 2 into n plus 1, right? Therefore, f of x will go as fast as x to the power of 2n plus 1 tends to 0. So that shows that f of x is big O of x to the power of 2 into n plus 1. You can check this using the definition that we have given for big O also, right? So in this case, we say that f is of order 2 into n plus 1. Well, after understanding all this, now we can see very clearly why we have preferred this form of the remainder in the Taylor representation rather than the one suggested by the Taylor's theorem. Let me again recall, as per the Taylor's theorem, we would have taken this as the remainder, but we prefer to take this as the remainder. Why it is so? Because this gives one order higher than this. If you recall, the series representation of cos x is 1 minus x square by 2 factorial plus x power 4 by 4 factorial minus x power 6 by 6 factorial plus x power 8 by 8 factorial, and so on. And in the approximation of cos x by the fourth degree Taylor polynomial, what we have actually neglected as the truncation error is going to 0 with order 6, right? As x tends to 0. That is happening actually in the formula. But if you stick with Taylor's theorem, you will see that your remainder term would have been sin c by 5 factorial into x to the power of 5 is what is coming actually from the theorem, and that is only going to 0 with order 5 as x tends to 0. See, one order actually less is what is suggested by the Taylor's theorem, whereas in reality, our truncation error is actually going to 0 a bit faster than what is suggested by the Taylor's theorem. That is why we prefer to take this form of the truncation error or the remainder term. So what you have to do is whatever function we give, first you try to write it in the Taylor series form, then take the polynomial up to the required degree and look at the truncated part of the series. Whatever is the leading term, its corresponding remainder term is what you are supposed to take, and that gives us the best information about how that error is behaving as we go closer and closer to the point A around which we are approximating our function. So this is why we prefer something slightly different from what our actual theorem suggests. Both are correct. You have to understand this. Both are correct. We are not doing something different from what the theorem is saying. Finally, we will define the notion of order of convergence. Let sequence an be a sequence such that limit n tends to infinity, an is equal to a. That is, sequence an is converging to the limit a. We say that the order of convergence is at least linear if there exists a constant c less than 1 and a natural number n such that modulus of an plus 1 minus a is less than or equal to c times an minus a for all n greater than or equal to capital N. That is, for sufficiently large n, the members of the sequence should be in such a way that an plus 1 minus an, that distance should be less than or equal to c. Remember, it is c is less than 1. Okay, times an minus a. It means the distance between the member of the sequence and the limit is shrinking as you go on increasing n, and this should happen after certain terms. Okay, sufficiently large n onwards it should happen. We say that the order of convergence is at least superlinear if there exists a sequence epsilon n that converges to 0 and a natural number n such that the same kind of condition happens, but now with epsilon n. Remember, epsilon n is converging to 0. Okay, so your distance is shrinking very rapidly in a sense, right? And that should happen for sufficiently large n onwards. Another notion that we use often is we say that the order of convergence is at least quadratic if there exists a constant c, not necessarily less than 1, and a natural number n such that this happens for all n greater than or equal to capital N. Finally, we define the order of convergence being any natural number alpha if there exists a constant c, not necessarily less than 1, and a natural number n such that mod an plus 1 minus a is less than or equal to c times mod an minus a to the power of alpha for all n greater than or equal to capital N. These are some of the important notions that we may be using quite often in our course. And this completes our first chapter on mathematical preliminaries.